I've always been interested, though, in discovery. That's always been a thing for me ever since I was a little kid.
In our solar system, we had a relatively quite violent, quite active first few millions of years.
Yeah, when I found out about meteorites, by the way, I mean, it was it was kind of life-changing. It was
one of the largest meteorite collections in the world.
Would you be willing to show me the process in the field?
I gotta tell you what, dude.
Are you sure you didn't just find a piece of the moon?
I'm not 100%.
Yeah?
Go this way. Go right now. Find out. Just go this way, quick. Okay. There's a big swarm of bees.
Oh.
They could be Africanized killer bees.
Oh. Okay. Yeah, let's go. My name is Noah Kennedy, and I'm an amateur video editor and journalist. I've been editing videos as a hobby, but I wanted to branch out into a more serious documentary-style content. I was given an opportunity in the late fall of 2022 when a cute gemstone shop called Cosmic Connections caught my eye. I met the store clerk, who then introduced me to the owner, a meteorite hunter named Larry Atkins.
My name is Larry Atkins. I hunt meteorites as a hobby, and I collect fossils, crystals, minerals, etc. And since I had to purchase this building for my poison ivy control, it had 2 units, so I decided to take the second unit and do something with it. So I turned it into the store. You know, I've just always been intrigued with the thought of discovery. So when I was in my 30s, I was about 38 years old or something like that, 36 or so, and I found out about meteorites. And already having had experience in fossil collecting, and I had an interest in space, it just was a natural fit for me. And as an outdoors person and a person that's been fairly successful in different sorts of hunting, whether it be animals or rocks or whatever, the meteorite thing was just sort of a natural. When I found out about meteorites, by the way, I mean, it was it was kind of life-changing.
I was immediately intrigued and asked Larry for permission to film an interview. He agreed and we filmed in his store the next week. After the interview, I asked Larry if I could accompany him on his next meteorite hunt.
Would you be willing to show me the process in the field?
While planning the trip, Larry introduced me to Laurence Garvie, a mineralogist and professor at Arizona State University.
My name is Laurence Garvie. I'm the curator for the Busek Center for Meteorite Studies at Arizona State University. You know, I've been at ASU for almost 30 years, been in the Center for Meteorite Studies for 15, 16 years, something like that. And I'm primarily a mineralogist. I study minerals. I'm quite happy to study minerals and meteorites. I'm quite happy to study minerals from outside. I'm quite happy to study, materials as well, man-made things. So there's interesting projects in all of these different materials. So in the meteorites, some of the meteorites have some weird minerals in. They're formed in environments that are very difficult to replicate here on Earth.
Larry was able to set a meeting with Laurence and myself at Arizona State University's private meteorite collection. With everything set out in front of me, I made the trip from Michigan to Arizona. I was off to film my first documentary.
So anyway, let me just say briefly, this is the Interdisciplinary Science and Technology Building number 4. So there's now 7 of them on campus. And so this building houses primarily some of School of Earth and Space Exploration and some various engineering departments as well. So anyway, this is the public display, which is obviously open to the public. We have thousands, 10,000 kids a year visiting here. And it's to give a flavor of the collection that we have here at the Busek Center for Meteorite Studies. It just gives a flavor. I put this display together. What do meteorites actually look like? You know, if you go online, especially if you go look at auctions or you go to museums, you know, you see big fancy cut slices which is, yeah, that's what people like to see, but that's not what they look like. There's a meteorite. That's from Arizona. It's Franconia.
Yeah.
With the one with the spider on it.
They're kind of ugly, actually, when you see
Yeah, it's a raw, stony meteorite from the ground. Haven't cut it open. That's actually a big sample.
So meteorites are named after the closest place name that would be visible on a map.
Okay.
So you look at a map, today we look at Google Earth pretty much, whatever, and then whatever place name is most prevalent and closest to that meteorite is what the name of the meteorite should be. So that's how it is. So usually they're named after a town or something like that. Maybe a mountain name. Like one of my newest ones, it's going to be called, most likely it'll be called Newman Peak. The reason is that the name Coolidge, which is the town that it's closest to, is already taken. Coolidge, I think it's Coolidge, New Mexico. There's a meteorite already named Coolidge, so there's no double naming.
That makes sense.
So instead, it'll be named after the mountain range that's right next to where I found the rock.
So, with the naming that you brought up, then why is this one called West Africa and
So
not like
that's
the specific town?
Excellent question. So here's the thing. So Northwest Africa, the Sahara Desert is the size of the United States. The people that find these meteorites in Northwest Africa, like that one right there, are nomadic peoples on camels. Okay, they're crisscrossing the Sahara Desert.
I have no idea what
They
found
pick
it.
these rocks up and they put them in a bag, and then they bring them to the market. Where did they find it? They know where they found it, but it's not it's not a recognizable official thing.
That makes sense.
There's no way to really prove or anything. So what they've done is the Meteoritical, the nomenclature committee or whatever, they've just come up with a simple solution, which is anything that comes from that area, if it's just a find that was picked up by a nomad, then it's just designated NWA, which stands for Northwest Africa, and then a number.
Okay.
In sequence. So right now we're up to like the 15,000s or so.
You have to when you think of meteorites have names. Like with anything, the name reflects the location that it was found.
Right. Okay.
But there's also a scientific classification. Yeah. So that one's called Imilac, but it's also and that's in relation to the location that it was found in Chile. But it's also called a palisite. And in scientific terms, a palisite, if you study meteorites, it immediately conjures up a type of texture and a type of mineralogy. So those are the two names for it. Same with that. That's a stony meteorite it's called Franconia, which is the location where it was found here in Arizona. But it's also another type of meteor. The type is an ordinary chondrite, and we can even subtype that classification as well.
So between Mars and Jupiter is where the asteroid belt is. Okay, the asteroid belt probably should have been another planet, but Jupiter's gravity is too powerful and didn't allow all those pieces to come together to form another planet.
Interesting.
So the planets go out, and if you look right here at my wall, you see Mercury, Venus, Earth, Mars, asteroid belt, Jupiter, Saturn, Uranus, Neptune. Okay. This thing is so big and it has so much gravity that it didn't allow all these pieces to come together to form a single body. So what happens is you've got all these meteors, asteroids, and they're all, every now and then they bump into each other. Boop. And by the way, they're traveling at huge speeds, okay?
Of course.
Incredible speeds up there. So now they bump into each other, and instead of just going around in its nice orbit around the sun, boom, it gets knocked off. Maybe it's going this way now, and another piece is going this way, and they could just be going willy-nilly every which direction. So we don't know when is a piece going to come in. It's not necessarily us traveling through a cloud. It's more of just a piece of an asteroid just off on its own crazy orbit around the sun, and then we run into it.
You have to remember, meteorites spent 4 point whatever billion, as asteroids or objects in space, spent billions of years under ultra high vacuum. We cannot create the level of vacuum in space in the lab, where we're talking only tens of atoms per, you know, an area like this. We can't do that. So these things were in this ultra pristine, ultra high vacuum for billions of years. Then they come to Earth. What's the first thing they do? Suck up the atmosphere. So what we try to do with some of the ones, like this is a carbonaceous chondrite, what we try to do is just keep them as pristine as possible. So I actually have a nitrogen cabinet in the vault, which we'll see in a minute, where, you know, again, it just keeps the moisture. If you know, whenever you smell something, whether it's cooking smells or perfume or bad smells, whatever, those are compounds that can be absorbed into some of these meteorites. It could make the analysis of the organic materials challenging.
Wow. This is intense.
So, welcome to the Busek Center for Meteorite Studies collection. It's one of the largest meteorite collections in the world, and it's definitely one of the largest, if not the largest collection in a state institute. And it's, I always have to say, it's primarily here for the students. The students are the ones that gain from having this collection here. So this gives an idea of what happens when a new meteorite falls. So if a new meteorite falls, or if a new meteorite is found, somebody has to do the science, somebody has to classify it. And when places that classify it have collections typically, but also have to have the analytical equipment to do the classification, to do the analytical work. In this particular case, this was slices of the one that fell in Muskogee. When did it fall? A few months ago. Yeah, 2 months ago or something like that. So what gets sent to an institute like ours is the type specimen repository material. This is material that will stay in here forever. There's other pieces out there that are in private hands and also in institutes. But then what we also then need to do, we need to take a representative piece and put it in epoxy and polish it flat. Wow. With diamond polish. So this is with diamond polish. And you can just see little sparkly, glinting minerals. Those are the minerals that have to be analyzed in order for the classification to be done. And then we look at the texture, we describe the texture, we describe the structures, we describe what I see, describe how many stones, what did they look like. So part of the classification is really, what is it? And it's only the first pass. It's not an in-depth scientific analysis that can come afterwards. This is what are the broad characteristics that allow us to classify the same? That's what a classification does. But anyway, one of the points is that what's called a type specimen repository, of which we are. So it's the Smithsonian. So are various other locations around the U.S. and around the world. These are places that have curated collections. We are type specimen repositories for new meteorites. And so that one fell just a few months ago. This one we're finally getting around to classifying. This is amazing. So December 24th, 2021, a stone about this big fell through just next to somebody's house in the most remote village in Uganda you've ever seen in Uganda. One person in the village had a cell phone. He tweeted out a photograph of a hole in his roof and a hole in the ground, and he's sitting there. I've got the video. The video is amazing. He's sitting there the next morning holding the stone with the other villagers. They're filming it with donkeys braying and goats walking around. And that made it out into the world. And then Mike Farmer, who's one of the meteorite dealers, who has a contact out there, bought the stone, and we're classifying it. So,
wow.
But it shows how small the world is. I mean, if you look, there's no roads to this village. There's some tracks.
See this is called basalt. It's an igneous rock that was created deep in the earth. Those mountains are igneous rocks made out of basalt. This is that. And you're going to see a lot of that. In fact, all this, you see all this stuff? This is all just ground down mountain.
Interesting. Over years of erosion.
Right. So when I'm looking for places to hunt meteorites, a lot of times I can just look at the surrounding mountains and know whether or not it's going to be a good spot. So if I look over and I see real dark rock mountains, I typically am not going to go hunt around those mountains because I'm looking for a dark rock. Why would I go to a sea of dark rocks?
It'll just blend it in, yeah.
Right. So if I look over and I see a lighter colored mountain, which around here you don't. They're all pretty dark around here. Yeah. But you know, you look for the lighter ground. So anyway.
That makes sense. That makes sense.
So then you get your eye on that, you see what it is, and you go, okay, I see what that is. Yep, I'm not going to pick up any more of those. Right? You don't even bother. But now, so real quick, let's just take a look. So I see a rock right there. I see a lot of little rocks. I might even hit that with my magnet just to see, you know, it's like, no, that didn't do nothing. I see holes in it. See that? See all them holes? That's another piece of basalt. No, meteorites don't have holes. You see that? So that's not a meteorite. As soon as you look down and see all them holes, you know it's not a meteorite right off. All right? Meteorites are solid. I look, oh, that looks like it's got some holes, but it's kind of the right color. Oh! What do we got?
No.
No, it's not a meteorite though, okay? So look, it's got a fair pull, but you see all them holes in it? Those are vesicles.
What does that mean?
That means it was in a basalt, it's a piece of basalt. Those vesicles are gas holes from it being in a magma chamber, like or a volcanic situation scenario. I'll tell you what though, I mean, it looks like a meteorite. It just don't quite feel like a meteorite. Feel the weight. It's a little on the light side.
Yeah, it's too light for how big it is. I feel like they're denser, right? What other stuff is magnetic around here then?
So that's high iron content. So you'll find basalt that doesn't attract a magnet, and then you'll find another piece of it that does. Okay? You're going to find out here possibly hematite, magnetite, basalts, these kinds of things. And, you know, magnetite's going to stick to a magnet, hematite typically won't. The basalt is... Sometimes it does, sometimes it doesn't. It just depends on its iron content. That's an interesting little piece, though.
How hard is it to determine where they fall if you see them?
So it's really difficult. It's extremely difficult because it's very, very misleading. To have an accurate determination of where you're going to find the rocks, basically you need witnesses or cameras from 3 different angles. So it's called triangulation. And so between the 3 angles, you can do a fairly simple math equation and estimate where on the ground the rocks are going to be. I'll tell you right now, that's the old way, and you know, people did it and were successful. But since then, new technologies come along. In fact, this guy named Mark Freeze, a fellow I do know him, he come up with an idea of using Doppler radar, or weather radar, to help track meteorites.
Interesting.
And, yeah, it doesn't always work. All the stars have to be lined up, so to speak. But if everything works out perfect, it makes it a lot easier to find the meteorites. And in fact, that's how I found the Hamburg meteorite in Michigan, was through Doppler radar, weather radar. I found the Osceola, Florida daytime fireball. We found that one with Doppler radar. A lot of the new meteorites have been found this way. So if you're ever watching the news, watching the weather, okay, and every now and then they'll show the actual Doppler radar. You'll see a screen, and there's like an arm going in a circle like this. And as it passes over a rainstorm or a thunderstorm, it'll show up as a bright green spot, okay? And if a meteorite comes and everything lines up, in other words, if this thing's spinning at a fairly decent speed, the rocks fall down, it makes a pass, and it actually picks up the falling rocks, and there's a reflection that gives a return, and it looks like falling rain. But it's not, it's rocks. But everything has to line up just right, because if the meteor comes in, the rocks fall, but the radar is still way over here and it's going slow, and by the time it sweeps around and makes the sweep and the rocks have already fell, it's not going to show anything. Or maybe it'll show the dust cloud, but the dust cloud's way over here now because the wind blew it. So it gets really difficult.
That's how it could be misleading.
Yes, okay. And it sends, I've been on, so more times than not, you go hunting and you don't find anything. And the reason is like that right there, you're not getting accurate information. But every now and then things work out really, really well, and you just go exactly right underneath the radar returns, and the rocks are on the ground right under the radar returns.
One of the reasons why we're getting so many falls now. Yeah. So a fall, we also have to distinguish a fall from a find. A find is like what Larry's been doing. He goes out, hunts for meteorites, and finds one that's just out in the desert somewhere, or wherever it happens to be. A fall is like, oh wow, look at that big meteor, and I'm hoping it drops some stones on the ground, like it did in Muskogee, and you go and try and find those. So they just fell, they're fresh, and so that broadly, you know, it's sort of an artificial definition, because sometimes, you know, so as an example, Indian Butte, was seen to fall in 1998, I think it was, but wasn't found for another 10 or 15 years.
Yeah, 15 years.
Yeah.
Interesting.
So
By the
it's-
way, my Aunt Laura found that stone.
Huh.
So what's
You
interesting,
got a family of meteorite hunters. Okay.
so what's cool about what I like in here, this sat on the ground for 15 years. So it gives us a good idea about how quickly something weathers here in the desert. So there's a little bit of orange to it. You can see where it sat on the ground for 15 years.
But other than that, it's in decent shape
Oh,
for
it's-
how long it's been in there then.
I'm surprised how much it weathered in 15 years.
Oh, you're surprised at how much it's
Yes.
weathered? Okay.
15 years. So it's a good time marker for weathering in our environment. And for somebody, like I who hunts for meteorites, having that knowledge about how quickly, like the one, that one that you left a slice of, it looks fresh. It couldn't have been on the earth for more than 100 years at the most.
So how long does it usually take you to find one? Or just does it vary?
So I'll give you an example. This last trip I just went on, I was 4 days in a place that it's an area that you could call it what's known as a dense collection area. It's a place where it's so perfect for hunting meteorites that a guy can walk out there and find a new meteorite in a day. Okay, it's that amazing. If you walk out here and try to find a new meteorite over in them mountains, it could take you 10 years. I'm not even exaggerating.
Wow.
You might not ever find one over there. There might not be one over there. If there is one there, you're going to be really hard pressed to find it because it's all rocky and it's dark rock, and you're looking for a dark rock in the dark rocks.
Okay, I see what you're saying.
So, and then for another example, the last cold find I made, or three cold finds ago, I made a cold find in Cactus Forest. It was 5 more winters before I made my next cold find.
Wow.
Okay? But then when I made that cold find though, I broke my losing streak, and this is last year. I found Newman Peak, I found Willow Beach, and now in the last 2 months, I've found like 5 new meteorites in California.
Wow.
So in a 1 year period, I found like 10 new meteorites.
Jeez.
But I had 5 years
Of none.
of
Yeah.
none. You see?
It's just give and take in how
It's
you're
well,
looking.
where are you hunting? Where are you spending your time?
Mm.
If you spin your wheels in this lava rock, you're
Not worth it, yeah.
You're really just out for a walk.
That's
You know what I
fair.
mean?
Walking for 10 years. Oof. Get in good shape though.
Oh, well,
I mean, typically you're going to have a single stone is going to come in. It's going to break into pieces, and all those pieces are going to be the same. Okay. However, that's not always the case. You can have what we call a rubble pile. So what if 2 different asteroids bump into each other up in space? They break into some pieces, and then through the millennium, through the millions of years, the pieces kind of come back together a little bit. They're not a solid stone anymore, but now you've got come together, the bits and pieces of 2 or more different bodies have now commingled all together. This thing comes into the Earth's atmosphere, breaks apart, and drops meteorites that don't match each other. That can happen. It has happened in the past.
Does
but it's
that
rare.
complicate things?
Yeah, in fact, what was it called? TC, I forget what it was called. Anyway, there was a meteor that was actually seen with a telescope before it came to the Earth.
Interesting.
It was spotted with a telescope. The astronomer did some quick math calculations, determined that it was going to impact the Earth. So then they were able to track the thing right in and prepare for it to hit the Earth.
That's crazy.
And then Dr. Jenniskens went over to somewhere in the Middle East, Tinduf, no, where was that? Anyway, I forget all the details now. But he went over there, got with the university and a bunch of university students, and they all went out and they found the meteorites. And it was like 6 or 8 different kinds of meteorites. And had it not been a witnessed event, I doubt that you could have convinced any scientist to write that up, that all these meteorites happened from the same event. They would have never done that. The only way that that was possible is because we saw it happen.
Would they
You
have
follow
potentially
me?
thought that was fake then?
No, they would have thought, oh, this is different events. this meteorite fell, and then this one fell, and then this one fell, because they're from different bodies. They're not the same kind of meteorites. How could they have come down at the same time?
I showed him a lunar meteorite, the Lyman one.
Yeah.
You know, here's one. So here's a lunar meteorite from North Africa, somewhere in North Africa. I'm not sure where. We'd have to look up the location. That doesn't even look like a meteorite. No.
You said a lunar meteorite?
Yeah, this is from the moon. And so I made some slices, beautifully fresh inside, but it's got caliche on the outside, so it's been part. It's probably, I'm going to guess, at least Pleistocene in age, at least 1 million years or so underground. It's got covered in caliche, and I don't know what the circumstances are that somebody located the first one on the surface. Somebody must have found an odd rock, found that it was a lunar meteorite, and then decided to dig and found more.
So this broke off of our moon. So did something strike the moon to make? Okay.
So the way we get, so here's a slice of a lunar meteorite.
This one's really impressive.
The way we get lunar meteorites on the Earth, as opposed to sample returned by astronauts, is by something large hitting the moon, ejecting material off the surface, and we happen to be quite close.
Could that skew what all is inside of the moon fragment with, like, based on the impact or something else?
What the lunar meteorites give us is a more random view of the moon. So from what I understand, when the astronauts went to the moon, they went to a geochemically anomalous area. I don't know any more than that. So what the lunar meteorites do, since it's just random hitting of the moon, and we happen to be quite close, whereas the study of the lunar meteorites is giving us a more general, and overall view of the mineralogy and the geology of the moon.
It's just a piece of basalt, but I have to look at it. Okay, so it's not the moon, but if you were to find the moon, it might look like this.
Oh.
You see that?
Mm-hmm.
Remember all the moon rocks we looked at yesterday?
Yeah.
You see the class?
Yeah.
See that?
It looks very similar to what a meteorite would, wouldn't
I
it?
gotta tell you what, dude.
Are you sure you didn't just find a piece of the moon?
I'm not 100%.
I mean,
It kind of feels like a meteorite right there.
it looks a lot like one. I will say, like, it looks like it fell in this direction, right? Like, came down.
Well, not necessarily, but so it's just a piece of quartz. I am gonna hold on to it.
Give it to Laurence, see what he
These are
says.
the kind that you don't immediately throw it back. It's like, it's got a couple characteristics going on there. You need a second look.
Here's a slice of Mars.
Oh my goodness. That is Mars. So, physically, the makeup of all these meteorites, like the lunar, Mars, and Earth ones, are they similar in chemical makeup?
Yes, so there's about 5 minerals in most meteorites. Let's forget the iron meteorites for now, because they're relatively rare. But there's a very small number of minerals that make up the bulk of the meteorites, and they're iron, magnesium, silicates. With aluminum and a bit of calcium, you know, a bit of sodium, whatever, a bit of chromium, manganese, a bit of the titanium occasionally. So they're normal minerals. So in particular, the Martian ones and the lunar ones. So if we think of the story of the early history of the moon was an impact plume from the Earth, so something impacted the Earth, and so it's geochemically very similar to us, but it hasn't had the long geological history of primarily water-rock interaction we've had here on the moon.
Right.
Sorry, here on Earth. Similarly, Mars has had a geological history that is younger than what we see typically in the meteorites, but it's still quite old. So when we look at the Martian rocks, they tell us about the geology of the surface right now. And the one that caught a lot of attention recently, just go behind me, is a meteorite called Black Beauty, because it's the first regolith. It's the first. So let's just step back a bit. The other, no, I didn't mean actually physically step back. I meant step back into my mind a bit.
I see.
So when we look at some of the other, when we looked at some of the other Martian rocks, they are igneous rocks that have been excavated from the subsurface by impacts. So interesting stuff. And we can look at grain boundaries. We can see evidence of clay minerals and things at grain boundaries. Tells us about water rock interaction on Mars. It was water seeping through the subsurface of Mars. Then we recently found a meteorite, a series of meteorites were found in North Africa that when they looked, that turned out to be Martian. And when they looked at the mineralogy, it's a breccia, it's bits and pieces. Unlike these, which are just single rocks.
Like
bits and bits. So it's like you scooped up some of the surface and welded it together from the impact and ejected it in space. So Black Beauty has a humongous diversity of components within it.
So scientifically and monetarily, it's probably one of the most valuable.
There's a $500,000 meteorite.
Oh my god.
Yeah, don't drop that.
Oh, okay, let's do this.
I feel like I should be wearing gloves for this.
Oh my god.
Yeah, it's a
Yeah, that's $500,000.
Yeah.
Can you imagine what this room is
I'm gonna
worth?
put this in my pocket. No, I'm just kidding.
Oh, you can go out. There's some for sale. Just go and buy it.
For 500,000, yeah.
Yeah.
Wow.
So that's the real. That's, you know, it's the story. It's the
Yeah.
story that tells about the surface and what's happening on Mars. And we have all these rovers that are wandering around, scraping and analyzing and collecting samples. So again, a great complement to what we see there. The rovers can analyze a relatively, you know, they trundle about slowly, so they can analyze a relatively small area. But the meteorites come from different big impact craters, so it gives us a better idea of the diversity of geology on Mars. Almost all the meteorites have a very specific age, which is 4.56 billion years old. Now, actually, there's a starting time to our solar system. Okay, let's go over here. I'll show you our solar system is defined by the oldest datable object, radiometric dating. So if you think of carbon-14 dating, carbon-14 has a relatively short half-life, so it can only really date things that have incorporated carbon-14, which then decays. We can only date things that have maybe less than 10,000 years, thereabouts. But we have other chronometers, other radioactive isotopes that decay much more slowly, have half-lives of hundreds of millions and billions of years, some of the uranium isotopes. So you can use you can use the decay and build up of daughter nuclei to age date old things. And so if we look at, here's a meteorite here. It's called a Yende. Found in 1969 in northern Mexico. If you look at that slice there, it's got some whitish amoeboid shaped objects. They're called calcium aluminum rich inclusions. And when we do radiometric dating of those, they are the oldest datable objects in our solar system. Doesn't mean there isn't something older, but they're the oldest things that we're able to date with modern techniques. And I think the age now is, you have to look up, there's a relatively precise age. It's like 4.5678 plus or minus 100,000 or 200,000 years error. Everything else in here that formed in our solar system is closer to us in time.
Then the calcium aluminum inclusions.
So they are so we define this, what are called CAIs, or calcium aluminum rich inclusions, as T equals 0. That's when our solar system started. Obviously there was a history before that, but we can't date that. So T equals 0. Everything else is now closer to us in time. Now it happens to be that almost all the meteorites that we have a relatively short formational history within a few tens of millions of years of T equals 0. And then our planets began to grow around that same time as well. And most of the planetesimals that these things derive from maybe were impacted and broke up, and we have remnants of them in the asteroid belt. We have remnants of them as asteroids. The main masses would have got swallowed up either by Jupiter or by the sun, maybe some of it impacted here on Earth. But yes, we had in our solar system, we had a relatively quite violent, quite active first few millions of years. the planets formed, or the planets were forming at the same time. Jupiter was probably much closer to the sun. We have various bits of evidence for that, and it then, for whatever reason, which I don't understand, migrated out to its current location in the solar system along with Saturn. And we've essentially been stable ever, for the last few billion years. Obviously, we've had activities on Earth. So as a result, when you age date all these meteorites, they all have an initial formation age of about 4.56 billion years old. Now, they could have had things happen to them afterwards. That clock can be reset through later impacts and things like that. Now, we do have some meteorites that are younger than 4.56 billion years, and those are meteorites that we get from the Moon and Mars. They've had a more recent geological history. This is the latest Martian fault. Yeah, Thyssen. This was seen to fall in southern Morocco a few years ago, and a number of stones were found. So this is a complete, I'll drop it, fusion-crusted Martian rock. Now, what color is Mars?
Red. As far as I can tell.
No, it's not. It's greenish.
What?
Yeah, it's greenish.
All the Mars rocks are kind of green.
They're all green.
Is that because of oxidization?
Yes.
Okay.
It's only the very, very surface. So if we look at Zagami, here's a nice slice. Here's a nice Martian slice. This is sort of a more. This is like more of a typical Mars color. It's a gray.
Interesting.
Just say green, using my imagination, but
It's got a green tint to it.
Yeah.
Has there ever been a confirmed Mercury meteorite that impacted on Earth at all?
There's not been a confirmed Mercury meteorite. So this is the paired one. There was this stone had certain characteristics, both bulk chemical composition, magnetic properties, that matched some of the messenger spacecraft that visited and orbited Mercury and mapped its composition. There were certain similarities between the two in the bulk chemical compositions that also are distinct from the other meteorites. So it led some researchers to suggest that this could be a sample from Mercury. I think it's not now widely believed, but it was a good proposition because it allowed people to really sort of then start to sort of figure out, well, what would a Mercurian or Hermian meteorite actually look like? What would we look for? What would be the characteristics?
Let me ask you a quick question. So it's been a long time since I read about CAIs, but I thought I remembered reading that they were older than the sun.
No.
Older than the sun?
No, that's pre-solar grains.
Pre-solar grains. So what he's referring to is that, you have to think there was something here prior to our sun. Our sun evolved from, the collapse of dust in a nebula, sort of in this interstellar cloud, which for whatever reason, there was some sort of gravitational instability or shock wave started to get it to collapse, forming a dense gravitational object, which was the sun. But there was still material there that was older than CAIs because it came from elsewhere. Because everything that you're seeing here, except possibly the hydrogen, everything here forms from exploding stars that lived and died. They had a lifetime. When they die, they eject the heavier elements that they made in their nucleosynthesis into their environment, out into space. So when they do that, they sometimes form little mineral grains that can survive the quite harsh environments of the interstellar medium. But it's amazing because when we look at the pre-solar grains, we can identify dozens of extinct star systems.
Is that right?
Hundreds even. These are stars that grew, probably had planets, grew, lived out their life, maybe became red giants and exploded into supernovae, ejecting that material out into the interstellar medium. That then sort of slowly aggregates as other molecular clouds that then sort of aggregate together to form other star systems. We're one of those, which is part of this immensely long, multi-billion year cycle that our universe is going through.
My excursion to Arizona was a life-changing experience. Arizona State University was an incredibly inspiring institute. Laurence represented his collection with pride, and his tour was full of incredible information. Laurence informed us of current missions to two asteroids named Bennu and Ryugu.
They had two missions. The Hyabusa, Japanese equivalent of NASA, they had two missions, Hyabusa 1 and 2, which actually observed two asteroids, and then actually touched down and collected material and brought it back. And the one that has been studied now is from an asteroid called Ryugu.
Ryugu?
Ryugu. It's black. It's very, very black. And so, but NASA also had the Osiris-Rex mission, which touched down on Bennu, collected material, and has brought it back. And that should be back in September.
Oh, so that was a relatively recent mission then?
Yeah, these are all recent. These are where this is cutting edge research that people are presenting now on these asteroids, where they're not just analyzing the meteorites that have fallen to Earth, but they're actually analyzing the sample returns from these asteroids.
As I've been finishing up the documentary, samples of Bennu have been delivered to Earth via Osiris-Rex.
This is from our high altitude cam.
PDL milestone. We have confirmed parachute deployment.
Wow, and after an exhilarating tour conditions, the team puts those into various models as they prepare for this key moment. The team on the WB-57 doing
PDL milestone, we have touchdown. I repeat, PDL. FRC has touchdown.
And touchdown of the Osiris-Rex sample return capsule. A journey of 1 billion miles to asteroid Bennu and back has come to an end.
Larry taking me on a meteorite hunt in the desert was unbelievable. Larry explained how treacherous the desert could be, as there are many dangerous creatures that claim the desert as their home.
Huh? Go this way. Go right now. Find out. Just go this way, quick. Okay. Let's go. There's a big swarm of bees.
Oh.
And they could be Africanized killer bees.
Oh. Yeah, let's go.
Real quick. I'll tell you. If they come this way, I'm not joking. Lay flat on the ground and don't move. Okay. They'll go right over top. I've had it happen many times. I told you the desert is dangerous. It wants to get you.
Yeah, it does. We spent most of the day in a large dried lake bed. Later in the day we moved locations to a petroglyph site, where I climbed a small mountain. This location was significant to Larry, as this is where he found Newman Peak. We hiked about a mile into the Sonora Desert, where Larry left a marker where he found the meteor. There are some fragments left over that I took home as a souvenir. After touring Arizona State University and meteorite hunting in the desert, I gained so much valuable knowledge. I learned so much about myself and where I want to be in life. I was able to get out of my comfort zone and gain many new experiences. I'm excited to see what adventures the future may bring.
Careful. Okay. She's about to lift up an iron meteorite. This is a tiny, tiny, tiny fragment of the one that made Meteor crater. Okay?
Oh
my God. Don't, if you drop it, jump back. No, if you do, jump back.
Oh, wow.
Oh, you got it?
Oh, my God. No. Yeah, I do.
Okay,
oh, my
good.
God.
I'm gonna try and pick this up too. Let me see this.
Can't believe it, huh?
Yeah, no, you're gonna do that.
It kept getting heavier and heavier and heavier.
Yeah.
Okay.
My arms are starting to hurt after that.
Okay. It's not that heavy, it's more of a surprise.
Oh wow, that's heavier than a medicine ball. That is really wow. That is very cool.
Do a handoff. I gotta feel it too.
Just
oh.
now, why haven't you found a new iron yet?
Laurence, I look.
You haven't looked hard enough. He hasn't looked hard enough.
Actually, you know what? I'm looking for. I find them like this all the time.
You do.
It's not big enough.
Oh, you want the bigger. You want the bigger.
It's not big enough.